Okay, so the first functional group that I thought we'd look at is carboxylic acids, from the carboxylic acids and its derivatives unit. Just for ease, I've kind of drawn it like this, but it doesn't show the bond angles or the shape around that central carbon, which would have been a 120 trigonal planar. So I could have drawn it, for example, like this. It might have shown it a little bit better, but for now, I'm just going to keep it in this original format, so it's just a bit easier to see. So carboxylic acids, they're able to act as acids. We know that acids are proton donors. We don't say that they are donators, that is not a word, but we can say that they are proton donors. And the reason is because that oxygen to hydrogen bond is able to break, and that oxygen atom is able to take both of the electrons inside of that bond. I'm using a reversible sign because it's a weak acid, to form C double bond OO with a negative charge, because like I said, it's taken both of the electrons in that bond, and our H plus. Now carboxylic acids, because they're an acid, they can actually react in the exact same way that you would have done at GCSE, with the kind of reactions, like I said, that they can undergo. So carboxylic acids, they are able to react with metals. They are able, I'm just going to abbreviate to COOH, carboxylic acids, they are able to react with metal hydroxides, which are our alkalis. They are able to also react with metal oxides, which are insoluble bases, and the second and final insoluble base that they can react with are metal carbonates. As I said, the reason that carboxylic acids can react with these things are because they are acids, and all three of these are examples of neutralization reactions. The thing is, we produce mostly the same types of products when an acid reacts with a metal hydroxide. There's only one slight change. So when a carboxylic acid reacts with a metal, we say a metal salt, but it's actually a metal carboxylate. So I always say to our class, it's our carboxylate salt and hydrogen. The next one, it's a neutralization, an acid plus an alkali. So I still would normally produce a salt, but this time it's a carboxylate salt and water. A metal oxide is an insoluble base, so it's still an acid plus a base reaction. So I still produce a carboxylate salt and water, and a COOH, once again weak acid, plus a metal carbonate, carboxylate salt, plus water, but also CO2 because it's a carbonate. So this is an example of a carboxylate. It's when we've got that carboxylic acid group but without the H+. So I can call this my carboxylate. So when I say a carboxylate salt, it's when I have a carboxylate and a metal ion with it. So let's put that into some practice. If I said to you that I have ethanoic acid, and I react the ethanoic acid with sodium, for example. Normally, if I had hydrochloric acid plus sodium, you'd produce sodium chloride as the root of the acid. You'd produce sodium chloride. I don't have that this time. I have sodium ethanoic. If I had sodium and ethanoic acid, there's no such thing as sodium ethanoic. But the way that we name carboxylate salts is they end in an O8. So what I would produce is something called sodium ethanoate. I'm reacting a metal and an acid, so that's this top one. So I also produce hydrogen. Same principle, let's try another one. If I had ethanoic acid, again, but this time I react it with sodium hydroxide. Actually, let's not use sodium. Let's say I use magnesium hydroxide. Let's say I go for that. I'll produce magnesium because that's the metal part. So I'll go for magnesium. And then it's a carboxylate salt that I'd formed. So I look at what carboxylic acid I had. It was ethanoic acid. The root I've just said for a carboxylate salt has to be an O8. So I have a magnesium ethanoate. It was adding a metal hydroxide to a carboxylic acid, which is this one. So therefore my second product is water. Same principle applies. I could keep doing this. I could go for a propanoic acid plus, let's go for calcium carbonate. I'd produce my water still. I'd still keep that part. I'd also produce CO2, and I also form a salt using the same principle. It's a metal carboxylate salt. Well, the metal that I've got is the calcium. I've got calcium, and the acid that it came from, the carboxylate, is a propanoic acid. So my root has to be propan. I know a carboxylate salt ends in an O8, so propan O8. So that's just writing those word equations for those kind of reactions. Obviously I haven't done the metal oxide as well. We'll very quickly look at your formula for it, and then that's pretty much our metal reactions in terms of our acid reactions in terms of reacting with different metals and their derivatives. So ethanoic acid is our CH3COOH. It's reacting with sodium. I'm not including state symbols in this, even though we know that we should, because the aim of this is not looking at can I write state symbols. Sodium ethanoate. So let's look at the ethanoate part. That's a carboxylate, and I told you a carboxylate has this root. So the CH3 part remains unchanged, so I can keep my CH3. The COO also stayed as it was, so I can keep that. But I've now got that negative charge from the ethanoate because I've lost the H plus. So I've got my sodium ion as well. So those charges actually cancel each other out. I can't draw this, just so you know, like this. And I can't draw that because that looks like it's a covalent bond when it's not. It's an ionic interaction or an ionic bond because it's between charges. Then I'd have to go back and balance out that equation. If I now look at the next one, ethanoic acid, CH3, COOH. This time I react it with magnesium hydroxide. I've got magnesium ethanoate. The ethanoate part, same as what we've done, our CH3COO for our ethanoate. But this time it's bonded to a magnesium ion. Currently, this would cause a problem. Remember, magnesium's in group 2, 2+. And it causes a problem because those charges don't balance out. So similar to what you've done in GCSE, we would need 2 of those ethanoates in order to have a total of a 2- charge and a 2+ charge. Plus water as my byproduct. I then have to go back and balance out that equation. And 2 sets of water. Propanoic acid, same principle, H2COOH plus calcium carbonate goes to propanoate. So our propanoate part is our carboxylate. We then know it's calcium. Calcium is found in group 2, so therefore a 2+ charge. While those charges aren't balanced, which means I need 2 sets of the propanoate plus water plus CO2, and now I need to go back and balance out that equation. But there we go. That's just your carboxylic acid reacting with metals, metal hydroxides, metal oxides and metal carbonates. The important part of this is that you're able to identify carboxylate salts because they come up later on as well. Hope that made sense.